All right, so now we start our final chapter, and sort of perhaps the most interesting for those of you who are of the aerospace concentration, the subjects of external flow is, of course, the material that comprises most of the aspects of, well, a phenomenon that has fascinated humans for centuries, right? Flight. And, this is a matter that has been object of legends and so on, and occupied the imagination of humans since history started. And in the beginning, the thought was always that humans could fly like birds. That was the original. Of course, imitating nature is the first approach to this problem. And it's quite a feat of engineering and human imagination to get to the point of this technology that we now almost take for granted, which is commercial aeronautics. Because all early thinking, of course, about flying concentrated on flapping your wings like a bird, right? So this is all that was available in the beginning as a thought of flying, and records that we have, of course, of Greek mythology and all that, all have to do with this idea that the humans could fly like birds. And of course, the most famous one is all of the studies of Leonardo da Vinci. He was completely fascinated by the idea of flight, and he studied the flights and the maneuvers of birds in very detailed way. His notebooks contain hundreds of drawings, sketches of possible ornithopter designs. The ornithopter is basically a machine that is able to, that has wings that flap, and somehow through a series of mechanical devices, the muscle power of a human is able to move these wings. So this was the idea, that human muscle power was going to be able to produce the required forces for flight. Apparently his manuscript contained in the order of 35,000 words that deal with this problem, and about 500 sketches. So he was completely fascinated by this. But the truth is that human-powered flight through flapping wings is something that technically was doomed for failure. The first human flight, as you most know, became a reality in 1783, thanks to hot air balloons. And so this is the first flight, the first human flight on a hot air balloon. It flew about 5 miles across Paris, and this became a sensation, of course. And it's interesting to note that balloons were the only means of human flight for almost 100 years. So, and also the technology of hot air balloons contributed nothing to the technology of current flight. It's completely separate and empirical. And so it really contributed nothing to our progress in powered flight as we know it today. And perhaps some of you may not be aware that the fundamental ideas of heavier than air craft, so separating out the idea of hot air balloons, that's sort of based on what we could call aerostatic forces, right? It's basically buoyancy, and we distinguish that from aerodynamic flight with heavier than air craft. The fundamental ideas of heavier than aircraft are, first, that you can produce this force of lift or sustentation by moving an inclined surface in the flight direction. First fundamental idea, and it's a great leap of the imagination compared to the idea of flapping wings, right? This is if you think about it now, we might take it for granted, but imagine what it was for humans at that time to leap to this concept that you could actually generate a force by just moving an inclined surface without flapping in the flight direction. Of course, this is associated with a second idea, which is fundamental, which is that power is required to compensate for the air resistance. These two ideas are crucial and fundamental, and they were put forth by Sir George Cayley in a three-part paper that he published in between 1809 and 1810. And this paper is actually, most of the time we think about the Wright brothers, right? The first who accomplished powered flight, as we know. But this guy actually published all the fundamental ideas about flight in 1809. So that's almost 100 years before it was accomplished. I think that is to get our head around that is pretty amazing. There's this book, I actually, researching for this lecture, found out about this book that tells about his life and accomplishments, and I became very interested, so I'm definitely buying this book for somebody for Christmas so I can borrow it. And I think it's very interesting to think about how this man could have thought about all of these, could have the insight about these things, because okay, what you see here in the drawings don't appear in this three-part paper that I'm mentioning, which I'll tell you a little bit more about that, and I actually found some transcriptions of those papers, and I can put them on Blackboard for you. He also had some very thorough notebooks that were published after his death, and in these notebooks you can find this study that he made of the cross-section of a trout, and this in the top is a reproduction of his sketches of that cross-section of a trout. And in the bottom is a superposition of that same profile with a section of a modern low-drag airfoil. And you can see, I think, a little bit of a difference, a tiny bit of a difference, almost imperceptible in this area. But it's quite amazing that he already had, within reach, the design of low-drag airfoils at that point, 100 years before flight was accomplished, powered flights by humans. Sir George Cayley, then, called the father of aerodynamics. Here's the portrait of him that is most known, a part of it. And so in this work of his called On Aerial Navigation, which I said was published in 3 parts, and I have found a reproduction, I'll put it on Blackboard for you, he had several crucial ideas about flight. The distinction between lift and propulsion that we just discussed, right? That the idea that you can generate the sustentation or lift, this force that is opposite to weight, by just moving an inclined surface in the direction of flight. And that you required power to overcome the resistance of air. Those are the two fundamental aerodynamic forces that are able to produce flight. The propulsion, that it needs to overcome resistance, so drag is already implied there, the force of drag, and lift, obviously weight, is the fourth force that we deal with when we talk about flight. So fundamental idea that he had in this work, the use of a fixed wing to generate lift, as I've already said. Fixed wing, this is a tremendous leap, because all history until then, thousands of years, of people thinking about flight was based on flapping wings, imitating nature. He states in this paper, for the first time in history, that lift is generated by a region of low pressure in the upper side of the wing. A fundamental idea. He also addressed flight control, the idea that you required additional surfaces, what we call today the tail of an aircraft, or the surfaces that control the yaw angle and the pitch. And he already had this concept, this idea of producing control. So it's a fantastic, really, contribution. In fact, not very well known for quite a while. A few knew about this, but it's very interesting that he published this in a mechanics journal at the time that had wide distribution, but it somehow didn't really become very, I mean, it was kind of obscure knowledge for quite a while. But the Wright brothers knew about the work of Cayley. And so, and through a couple of others that knew his work, this did disseminate. But it took 100 years before these principles were actually used to accomplish flight. These are some of his drawings. This is one of the drawings that appears in the first part of his paper, where he describes the forces of lift, propulsion, drag, and so on. And this is his drawing of what he called the boy carrier, because he wasn't able to generate enough force to put an adult on this. He was only able to basically fly with a 10-year-old boy or 8-year-old boy that actually, I don't know how their parents allowed him to or maybe I don't know, it was a family member that he put on this little boat here. And this was a triplane. Actually, if you notice in his drawing, there's 3 surfaces generating lift, and already you have, these surfaces that help control the craft. So this is actually the origin, the real father of human flight and aerodynamics, Sir George Cayley. Very interesting read, actually, preparing for this lecture, to remind myself of this the accomplishments of a man that was a very, very prolific engineer. In fact, he also invented the caterpillar, the concept of the caterpillar, the traction that tanks have, and he never capitalized on that idea. It's very interesting. So, let's see. Going back to, so these papers were published in the beginning of the 19th century, right? His three-part paper, 1809, 1810. So for almost 100 years, there was this kind of lull in the progress in this subject. But the basic problems that 19th century flight theorists had to deal with were two problems. One, how to determine the power required for flight. Remember, Cayley identified that we had to generate some power to overcome the resistance of air to be able to move an inclined plate, which will generate the lift. So what is the power required for flight? Basic problem. And the second problem that occupied 19th century enthusiasts and mostly enthusiasts and empirical, workers rather than scientists and mathematicians. This at this time was developed completely as an empirical science, was to find the most efficient shapes for wings. So let's talk about this first problem. The power required for flight. Of course, the power, so all of these studies at the time were developed through observation of birds, looking at nature to inspire the progress of engineering. And the most interesting observations came from looking at what's called soaring birds, birds that are able to glide. And the question was, what is the power required for a soaring bird to maintain a fixed altitude? That's the first question. So the power required for flight. There are 2 quantities that were recognized to be important in this question. One is the ratio between the weight and the wing area. So this is weight divided by wing area, otherwise known as wing loading. And the other quantity is the ratio between the weight and the power available. The power loading. For bird flight, of course, the power available is the muscle power of the bird, the muscle power that the bird can exert during flight. And one may assume for the bird that this muscle power is somehow proportional to the weight of the bird. So more muscle the bird has, the more power it can exert. It's kind of the reasoning of the time. Does that make sense? Okay. So the main question here is to estimate the power required for flight and compare it to the power available. If at the time the thought was of being able to generate flight through the muscle power of humans, then the first question is to estimate the power required by observing birds and then extrapolate this and see how it compares to the power available in human muscle and see if that made it possible. So for the power required, the first thing to look at is the situation of a soaring bird. So this is a bird that is just gliding along, and the question is, if the bird is just soaring, right, without flapping its wings, it's going to be actually flying in a certain direction, and it's going to be dropping in altitude. Basically, it would lose a certain altitude in unit time, and this is called the sinking velocity. This is a bird gliding. We call them soaring birds. So the question is, how does the bird manage to fly horizontally? The bird will obviously flap its wings every so often and thus impart some power to his situation, and the bird will probably do this just as much as necessary to raise its body to overcome the sinking velocity. So the bird will want to every so often bat its wings to recover that altitude that it loses naturally as it glides. And so this is the only possibility to fly horizontally. Just as much power is necessary to counteract the sinking velocity. Right? So, in fact, this leads to an estimate that the power required per unit weight has to be proportional to the square root of the wing loading. The wing loading is W over S. So basically, so power required per unit weight, notice, is kind of the inverse. It's exactly the inverse of the power loading. So if I write this again, it'll be P over W has to be proportional to the square root of W over S. Well, this argument led to that estimate. So, some more detailed analysis. We're already in 1889, so 80 years after the publication of Cayley's famous paper, and still, progress is very sluggish in this matter. Charles Renard, a Frenchman, he expressed the power. He did the following. He expressed the power required for level flight as the sum of the power necessary for sustentation and the power necessary for propulsion. The power necessary for propulsion being equal to the drag multiplied by the speed. Force of drag times the distance divided by time is power. Then he computed the velocity at which the power required is a minimum. And he obtained with this P over W, the power per unit weight, equals to a constant times square root of weight over rho and S. So we have the density of the air coming into play here, and this is the wing loading. And this constant then was to be found by experiment. So with this progress, with this understanding, then it's interesting to see how the wing loading of birds, of many different sorts of birds, actually changes with their total weight. And how does this look like? Yes?
That drag times speed is the sum of both.
No, it's just this one. The power needed for propulsion. The power needed for propulsion is excuse me? Sustentation. Another word for lift is the word that was used at the time because it comes from the the tradition of the hot air balloons was that the vertical force was the sustentation that was obtained from buoyancy, and so it remained the word in vogue for this vertical force. And now we call it lift, of course, but it's still, in kind of the historical discussion that we're having, then many books you'll still find the word sustentation. It comes from the ballooning sort of tradition. So we required power for keeping our altitude and power for overcoming drag is what this is. This is the total power required. and the power required to overcome drag is equal to the drag times the speed. That's the bottom line of this progress by Charles Renard. So now that this understanding exists, let's look at the wing loading of birds. Okay, I have a little picture that appeared in a book that was published by, like, sort of kind of historical little book in aerodynamics published by the famous Professor Theodore von Karman. It appeared in 1954. This book, you can get it quite cheaply now in Dover, in one of these Dover reprints. And he did a little bit of he collected, of course nowadays there are many of these sort of plots like this, but this is the first one that appeared, I believe, in print in 1954. And he looks at the wing loading here, so this is wing loading, and this is the weight in pounds. And he collected information from some books that were completely from biologists and so on, books. He collected this information and organized it for the first time in this manner with the help of people, ornithologists and so on, as he describes in his book. And he has a number of different birds here. Okay, and this is, notice, it's a logarithmic scale. Okay, and all the birds here in this logarithmic scale, the wing loading versus the weight. Okay, and so in general we can say that the wing loading increases as the weight increases. You can see that as much. We can say there's no clear relationship, but as the wing loading increases, the weight increases. But think about the implications of this. This is a logarithmic scale, and since the power which a bird can exert with the muscles is approximately proportional to the weight, then this, so let's be careful with this argument here. So the power which a bird can exert by its pectoral muscles oops, bird, no, it's a bird. My I'll get to that in a moment. Ignore the line for the time being. I'll explain it in a second, okay? For the moment, just look at these dots and agree with me that the wing loading increases for the time being with weight. Sort of, approximately, or let's just say in general, because this is not approximate, it's just a very qualitative observation. Wing loading increases with weight. Okay? And then we make the following argument. The power which a bird exerts with its pectoral muscles is approximately proportional to its weight. We've already introduced that idea, and it makes sense. The more muscle mass, the more power, of course, available. So it's proportional to its weight. Yet the wing loading increases with weight in this quite fast, because this is a logarithmic scale. So the wing loading increases much faster than proportionally, which means that flying becomes more of a problem as for bigger birds. Flying becomes harder for bigger creatures, because as the larger the creature, the more the wing loading that is required, while the pectoral muscles only give you a proportional increase. You see that thought? So The bigger the bird, the harder it is to fly. The conclusion of this argument is that there should be a certain size beyond which living creatures cannot fly. There should be a limit to natural flight by muscle power. Think about that for a moment. Yes? You see the argument? Okay. Perhaps some of you are familiar already with this, but perhaps some others are not. So let's carry on. So far, we come to an interesting conclusion, which is that beyond a certain size, living creatures are not going to be able to fly because of this situation that we see from nature. We just extrapolate this. Now, there is a very interesting observation that was made by the German, and I've run out of time, so space here, so let me just write it up here. Helmholtz, professor in Germany, in 1873, he proposed a similarity law for flying animals. This similarity law was that the weight of the animal would be proportional to the cube of its length scale, which makes sense. The weight proportional to the cube of its length scale, because the length scale to the cube power is sort of the volume, so that makes sense. And the wing area proportional to the square of the linear dimension, so that makes sense as well. So with this thinking, that leads to a wing loading result, which varies proportional to the cubic root of the weight. And that results in, the cubic root of the weight results in a straight slope of relationship 1/3. So this line here is a line of slope 1/3, 1/3 slope on the log-log scale, indicating that the wing loading increases proportional to the cubic root of the weight. And what's interesting to note is that this 1/3 similarity law of Helmholtz really only applies well, or mostly follows the wing loading of the soaring birds, with the exception of a couple of other ones, like the crow appears in there, not a soaring bird, but a very effective flyer. And the wing loading of the right flyer is around here. Of course, the weight can vary depending on how much, how heavy the pilot is, but it's around here, this level. So, Helmholtz, of course, came to the conclusion that humans could never fly by their own power. He was convinced of that. There's an old legend in the field that he asked a student in an exam whether humans could ever fly, and apparently the student did not give the right answer, and so he was flunked because Helmholtz was completely convinced that humans would never fly. So this is the state of the knowledge in the 19th century, and brings us to, it's just fantastic to think that George Cayley already had this concept of the four forces of flight, and we will discuss this. Let's take a little 10-minute break now at this point. We will discuss the forces of flight in what follows, and jump a little bit to how, the knowledge that we have today about this subject.